welcome guys. So in this video, let's talk about this Bessels inequality. Everybody knows about Cauchy-Schwarz inequality, and many inequalities like Cauchy-Schwarz inequality can imply the triangular inequality. So let's talk about many inequality in the Hilbert space. So one important inequality is called the Bessels inequality. So theorem that H be a Hilbert space that maybe E1, E2 up to countable, also normal sequence of of H. And for any vector in Hilbert space, then the x dot with ek square, k from 1 to infinity, will less than x squared, normal of x squared. Okay. So basically, this theorem tells you that if you choose like how infinite basis or finite basis, also normal, and it's obvious that the length of these vectors, the norm of length of these vectors will be greater than or equal to each component, right? Each sum of each square component. Okay, so this theorem is very intuitive. Okay, so proof is very easy. Yeah, I already write down details. So let's x prime, right? Let x prime to be x ek k from 1 to infinity, right? So by definition, you x minus this x dot with ek k from 1 to n, let's say n, right? Up to some n. This n can be infinity, right? And take a square. Then become then we want to compute this, right? So for the simplicity, let's say a to be x, b to be this guy, okay? So it's a minus b in a product, so it's a minus ab minus ba plus bb, okay? So the first term is x squared, the second term is a dot with b, right? So these two dots is x ek squared, okay? And ba is the same, x ek squared. And this is the cross term, right? So remember the cross term, and we have two sums. But we already say that ek is also normal, so ek ej will be delta jk. So by definition, it becomes this. So finally, we get x squared minus k x ek squared, k from 1 to n, which is greater or equal to 0. Greater or equal than 0. Okay, so you can let the n to be infinity, and you still get this. So this is the famous Bessels inequality. And if the E1, E2 up to infinity is complete, so basically if you think this H is just a complex Hilbert space, then your x squared becomes this. Then this will just be equality. So for example, in the Fourier analysis, you can take f to be L2 squared, so f squared dx. This is the inner product, and then this Cn is Fourier coefficient, right? So by definition, your length square will be Fourier coefficient square, right? And then there is just up to 2 pi. Okay, so that's it. I will see you guys in the next videos.